Urban air mobility expands the concept of urban mobility into the airspace. This new mode of transportation presents lots of challenges as well as opportunities to companies and engineers around the globe.
Mit den Flugtaxis der Urban Air Mobility entsteht gerade ein sehr, sehr interessanter Markt für die Mobilität der Zukunft, der aber auch viele technologische Herausforderungen mit sich bringt. Es geht darum, die Leistungsfähigkeit der Strukturen, wie wir sie aus dem Flugzeugbau kennen, mit der Großserienfähigkeit und der Effizienz, wie es der Automobilbau typischerweise mit sich bringt, zu kombinieren.
Fraunhofer researchers support companies to find new ways to engineer efficient and sustainable air transport systems. BTfly. Researchers have created a graph-based design language to generate lightweight beam structures for urban air vehicles. The user selects one of multiple options regarding material, stacking, and shape. Then, the design program computes an individual beam structure variant which delivers stiffness, strength, and stability during all flight conditions.
Im Entwicklungsprozess ist es für uns besonders wichtig, dass wir mit diesem Tool des Wissensmanagement die Möglichkeit haben, viele Varianten zu betrachten. Wir können also unterschiedliche Flugzeugkonzepte oder Fluggerätekonzepte mit den Fertigungsverfahren im Hinblick auf Kosten, im Hinblick auf Sustainability oder Risiko bewerten und damit zusammen mit unseren Entwicklungspartnern einen großen Mehrwert schaffen.
Changes to the design result in fundamental changes at every phase along the beam structure's life cycle. This affects the entire process chain and process parameters in manufacturing, the flight behavior and energy consumption in use, and the recycling process parameters and resulting emissions in end of life. To assess these aspects, Fraunhofer researchers have developed evaluation modules. They allow an automated and detailed evaluation of the component's performance, environmental impact, and costs from cradle to grave. By connecting the lifecycle evaluation modules with the beam design language, numerous design variants can be computed and compared. Each variant offers a unique trade-off regarding its performance, environmental impact, and costs. Engineers need to weigh and prioritize their design goals and eventually select the most promising variant. By doing so, they can decide fast and smart with regard to all relevant design goals. Afterwards, further details of the beam structure are designed, such as the rotor integration assembly. For the design of the rotor integration assembly, a topology optimization algorithm is applied, resulting in an efficient, organic-looking structure. Such complex parts are frequently produced with novel additive manufacturing methods, such as 3D printing. After completion of all design and evaluation steps, the final beam assembly can be integrated into the overall aircraft design. Graph-based design languages enable experts across disciplines to quickly compile and evaluate numerous different product variants without great manual engineering effort. Beyond urban mobility, this approach can contribute to the transformation of the aerospace industry, including hydrogen-powered and electric flight, digitization and networking, intelligent manufacturing, and biological transformation.